Welcome to Spring LIB.
Okay, you can prove that two compounds are different by TLC, but you can't prove the two compounds are the same. Why is that? Well, consider that all you can do with TLC is determine how far up did my spot move. You get your RF, you get the how far your spot moved in centimeters, like X centimeters over how long the solvent was in terms of centimeters. So all that, it's like one-dimensional information, right? And then you get your spot to tell you, like, oh, okay, it got that far up. Well, if let's say two compounds have a different RF, right? And I've got one here, and then I've got another compound, and my other compound uh, gets that high. That's all well and good, right? I can say, okay, this spot is clearly different from that spot, so they must be different, right? It's like if they don't have the same RF, they must be different. Because if you run a TLC and let's say you like started with green and both times, then you'd end up with the same exact distance for your spot, right? That's just, you could run the experiment a million times. This green dot is always going to end up in this final green dot position. The issue you run into with proving that two compounds are the same is that, let's say, okay, so in the case of green versus blue, I showed blue having like a higher RF, right? Oops, I should have drawn this, right? So I can prove that they're different because I know that green is always going to be right here and blue is always going to be right there. But what if I have a bottle of green stuff and a bottle of red stuff, and the green stuff, I think there's something, I think they're the same compound, right? But the green one spots here and the red one spots here. They have the same RF, right? Well, how can I determine? Remember that the green is just a stylistic thing, and in actual fact, all of these dots will be black, right? So there's no way that I can distinguish between the green and the red, right? Because they're not green or red in real life. We're just using that to signify that maybe the green stuff came from bottle A and the red stuff came from bottle B, and I think bottle A and bottle B are the same compound. I run them both, and they both come up at this line, and I'm like, yeah, that proves A and B are the same thing. Well, not necessarily, right? Because it's entirely possible that they're two different compounds that just happen to have the same RF value. That can happen all the time in a million different ways. An example might be if I have like an R enantiomer of some alcohol, and then I have the S enantiomer of that same alcohol. They're not the same, but their RF would be strikingly similar. I mean, it would probably be exactly like this, where they just appear at the same spot. There's no way to prove that they're the same molecule, and in fact, in this case, they wouldn't be the same molecule, but they would look like it, or at least as far as TLC could tell, because the spots are going to be at the same spot. That's the only proof that you can get. The only thing you can really show is that the RF values are the same, but RF values being the same doesn't mean the compound is the same. Why is it necessary to analyze known compounds when performing TLC analysis? Basically, you want to have something to compare your unknown to. So in a way, the known compound can serve as a standard. You could compare, A to B, and you could at least prove that they're not different, right? As we saw with green and blue, right? We proved that they're not the same compound. Well, that's helpful when you know exactly what B is, right? It's like if I have A and I expect it to be different from something else, I can run that other thing to give me something to compare to.